Okay, so we're on to 10.2. In this section, we are going to talk about measuring energy expenditure. And so energy expenditure can be measured or it can be estimated. And so we'll talk first about measuring. We can do this directly or indirectly. So direct calorimetry, so again, the amount of calories being used, can be measured directly by looking at the amount of heat released by the body. And so 60% of the energy that the body uses eventually leaves as heat. And so again, that can tell us, how many calories are being burned. How do we do this? First off, this is a very expensive and complex method. And so it's not the preferred or most common method used, but it is the most direct method used. And so we can do this by measuring, by placing an individual in a chamber about the size of a bedroom. It's an insulated chamber that is surrounded by layers of water. And so what is measured is water temperature before and after the body releases heat. Okay, and so again, the heat that's released determines the amount of energy that the person has expended or used. Okay? So again, that's direct, it's expensive, and it's complex. An indirect method that is more commonly used is going to be just the collection of exhaled or expired air from an individual during a specific amount of time. And so there is this predictable relationship between the body's energy expenditure and the amount of oxygen consumed and carbon dioxide that is released. And so again, measuring the amount of carbon dioxide released in that expired air will tell us how much energy that the body has used. Okay, so again, an indirect method. We can also just estimate energy requirements. Okay, so again, how many calories does an individual need? Let me actually go to the next slide first, and then we'll back up. You've actually seen this table before, back in a previous chapter. So when we estimate energy requirements, again, how many calories an individual needs per day, that's going to be based on a multitude of things, but in this particular figure, it's based on biological sex and age. Okay, so we have children, females and males, and then we also take into account the activity level of the individual. Okay, so for example, if we have a female who's 32 years old, this would be, so females is here, 32 years old would be in this age bracket, and let's say that this individual was pretty sedentary, didn't do a lot of activity, that individual would require about 1,800 calories a day. Okay. As activity level increases, the number of calories required increases. And so a very active 32-year-old female may require around 2,200 calories. Again, these are rough estimates. So if I back up one slide, a better estimate that's a little bit more accurate, not as accurate as calorimetry, but a little bit more accurate, we need formulas. It's the same idea as we just saw in the table, but there's a formula that takes into account height and more specific activity levels. Okay, so we're looking at the person's weight and height, biological sex, age, and activity level. So again, there's more factors when we use these equations. The formulas to calculate EER using this method, which again takes into account weight, height, and more specific activity levels, they're going to be found on page 342 of your textbook. So I didn't give you a whole list here. Instead, I just walked through one example. So in this example here, we have a 25-year-old male. He's 5 feet 9 inches tall, and he weighs 154 pounds. And he's active. So there's that first word there, active. Okay, so for activity level, we have an active. So the first two things you need to do is these formulas use centimeters for height, and they use kilograms for pounds. And so that's the first thing, two things that you need to do. So to convert inches, or feet and inches, to centimeters, so first we have to convert to inches, and then we take inches times 2.54. So there's 12 inches in a foot. So an individual who's 5 feet tall, we do 5 times 12 to convert that to inches, and then plus the 9 inches that we already know are also there. And so 5 times 12 plus 9 equals 69. And so this male is 69 inches in height. We have to multiply that by 2.54 to get centimeters. Okay, there's the first conversion. The second conversion we've done already. So to convert pounds to kilograms, we just divide the pounds by 2.2. So in this case, it'd be 154 divided by 2.2. So this male weighs 70 kilograms. So now we have height in centimeters and we have weight in kilograms. So here's the formula. Okay, so again, this is based on an active male. Okay, that's where these numbers come from that are already kind of in here. Depending on activity level, these numbers would shift. Oh, and biological sex. Okay, so for an active male, we would have 1004.82 minus, and then in parentheses, so this needs to be done first, 10.83 times the age. And so this guy is 25 years old. Plus 6.52 times his height in centimeters, so 175.26, plus 15.91 times his weight in kilograms, 70 kilograms. So if you do this in the correct order, so you have to follow order of operations, you would come up with 2,990.5 calories. And so that's the number of calories that this individual requires to not just meet his basal metabolic rate, but to also meet his activity level. Okay, so again, a pretty accurate estimate, taking into account multiple factors. So let's go on to eating behavior regulation. So this is 10.3. So there are two factors that drive our desire to eat. They are hunger and appetite, and they're definitely intertwined, interrelated. Hunger is going to be the physiological drive to find and eat food, and it is controlled by internal mechanisms. So organs, hormones, hormone-like factors, nervous system, neurotransmitters, they're going to control hunger. Appetite, again, is the physiological drive to eat, but this time it's controlled by external factors like social customs, time of day, what mood we're in, if we're stressed out, memories, sight of tempting desserts. And so again, these are intertwined, but they don't always coincide. So you could be hungry, right? You can have those internal cues of hunger, and you may not have an appetite. Or you may not have internal cues of hunger, but you still might feel this drive to eat because you have an appetite. Okay, so again, they don't always coincide, but they are intertwined. And at the bottom here in this figure, it just shows some of the things that trigger hunger, and then some of the things that trigger appetite. Okay, satiety. We've mentioned this term a few times. Let's make sure we define it here. So satiety is the state in which we feel satisfied and we no longer have the drive to eat, okay, whether it's hunger or appetite driving that. This feeling is regulated by a region of our brain called the hypothalamus. The hypothalamus communicates with the endocrine and the nervous system, and it integrates many internal cues, including blood glucose levels, hormone secretion, and the hypothalamus can both inhibit and encourage food intake. And so there's going to be this region, here we go. So if I'm in the brain, here I am right here. This is the hypothalamus, which is above the pituitary gland. If I blow this up, right, pituitary gland kind of is the gland that kind of hangs off the bottom of the brain. Here's the optic chiasma, which leads to our eyes, okay, and then we have our hypothalamus, which has a bunch of different regulating centers. But again, one of them is the satiety, and if we look up here, this is the hunger center. So they're just two different regions. Internal signals that stimulate the satiety center of the hypothalamus cause us to stop eating. And then if internal signals stimulate the hunger or the feeding center of the hypothalamus, that's going to trigger us to eat more. So we do have these signals, and we do have this region of the brain that kind of controls that. However, we can override internal and external signals. So, we've all done it. You're eating dessert on a full stomach. Your hunger center in your hypothalamus is not activated, and yet you're eating, okay? Or we can ignore hunger. and if we don't have the appetite for food. Okay. Okay. So the process of satiety short term is here. Okay, so feelings of satiety are brought on first by the sensory aspects of food. So flavor, smell, size or shape of the portion, the variety of the different foods on our plate. When we chew our food, that causes the release of histamine, which again affects the satiety center of the hypothalamus. And then when we swallow our food and the food moves into our stomach and into our intestine, those organs expand. That's called gastrointestinal distension. And that's going to also trigger satiety. Lower energy dense foods, so foods that are high in water, fiber, so I think fruits, vegetables, okay, they promote satiety to a greater extent because they create a larger level of gastrointestinal distension. Okay, so again, that stomach and intestine expands and that triggers satiety. And then there's the effects of digestion, absorption, and metabolism. So secretion of hormones during these processes, nutrient receptors in the small intestine as they bind to nutrients, that's going to trigger satiety. Apolipoprotein on chylomicrons, okay, those are going to trigger satiety. Neurotransmitters like serotonin, those get released during these processes, and they trigger areas in the brain which cause calmness. Decreased hormone ghrelin. So ghrelin is the hormone that triggers, hunger. It is secreted by the stomach, so those levels go down. And then nutrient use in the liver. Okay, so that's 4. Influence of nutrients in the liver and related communications with hypothalamus and other regions of the brain. And then 5, conscious thinking takes place in the brain's cortex and can overcome hunger signals or satiety signals. Okay, so that's short term while we're eating. Long-term satiety is a little bit more complex. And so long-term satiety is actually promoted by body composition and the amount of fat. And so adipose tissue, which is fat tissue, it secretes a hormone called leptin. And leptin causes reduced food intake, reduced weight, and reduced body fat. Okay? This is a little bit nuanced. So leptin is controlled by a gene called the obesity gene, the OB gene for short. And it's been found that individuals who have a mutation in this gene have reduced levels of leptin. They have a dramatic increase in the desire to eat, increased food intake, a decrease in metabolic rate, so a reduced energy output, and weight gain. However, it has also been found that many people that have obesity actually don't have this mutation. They actually produce high levels of leptin, but instead they've become leptin resistant. So leptin isn't working how it's supposed to be working inside their bodies. And so treating these individuals with leptin doesn't cause weight loss. So again, this is a little bit of a nuanced area, but it has been shown that leptin reduces food intake, reduces weight, and decreases body fat, but can't be used as a treatment for obesity. Okay, signals to eat. So several hours after we consume a meal, the concentration of macronutrients fall and the body starts to use energy from its stores. Okay, so we're going to be using glycogen for glucose. We may start to use triglycerides from adipose tissue. Okay, this causes the feelings of satiety to decrease. And those feeding signals, that feeding center in the hypothalamus becomes more dominant again. There are hormones that stimulate appetite and increase food intake. Again, we've already mentioned ghrelin. Ghrelin is produced by the stomach. It will rise before a meal and fall after a meal. And then we also have cortisol, which is produced by the adrenal glands. Both of these stimulate appetite. Okay. up with part 4 in the next video.